Good evening, everyone.
Good evening.
Good evening.
Good
How are
evening.
How are you all?
Good. How are you?
I'm good as well. Thank you for asking. So, did you guys do the homework? Did you look at the homeworks, or didn't get time to look at the homeworks yet? Okay,
Just
but like,
glanced at it.
yeah, okay, good. So you have access to, everyone has access to book, right? Yeah. Okay, good. Good. Okay. So today we are continuing of what we did on Tuesday. And like, let's see, we are 1, 2, 3, 4, 6. So we are 10 here. Okay. So okay, let's wait for another minute and then we can start. I might get an email saying. Okay, so let's start. I hope like they will join on time. Let me share my screen, my iPad. Yeah. There you go. Yeah. Nice. So rearrange my screen. Okay. So yesterday we did here yesterday's note. So I have posted this in a Blackboard as well, just in case if you guys need it. So these notes are okay, and in the Blackboard as well. So we did the significant figure, rounding up the numbers, right? And also we did like a scientific notations, right? So how we can write down the scientific notations. So basically here, uh, scientific notation, right? What the scientific notation means? So basically it is estimating in the terms of power of an order. So suppose if we say 200, we can also write down equivalently this is 2 times 100, which is same as 2 times 10 to the 2. Okay. So, and same thing like, if 2000, you can also write down this in 20 times 100 equals 22, right? So, so this way you can write down. So now the difference between this one and the first one and the second one. So this one is, so here they have the same order of power, but the magnitude here is different. So this will give us a very clear idea. So looking at this, oh, this is 10 times more than this one. Okay. So this same thing you can also write down. And also this is called a significant figure. So in this case, it has a 2 significant figure. It has a 1 significant figure, right? So again, if you want to write down in terms of like 1 significant figure, you can write 2.0 times 10 to the, so this is 2 times 10 to the 3. right? So these are like a part of notification. And also I would like quickly like to go through this. Yesterday we talked about the error, right? Uncertainties. So before we go jump into the next section called vectors, I'll just continue on this one, this error. So now estimation of error. And this is what we're going to use in our lab as well today, the estimation of error, right? So whenever we measure any physical quantity, right? So we measure the physical quantity in their magnitude and in their units. And then whenever we measure something, we always have certain uncertainties, right? If we have like certain uncertainties, okay. So the way we write the uncertainty is, if we measure a quantity x, this x is measured as a x plus delta x, where uh, delta x is the uncertainty, right? And then so suppose if you are measuring like two-dimensional object, like the length and width of a table, right? In that condition, so like say another measurements we did, so y, and which has the uncertainty of delta y. So this is again another uncertainty, right? So now to calculate the uncertainty, now we know if we just do like one measurements, yeah, easy to do it. But now what if we are doing an addition? Because in physics, a lot of the times, what do we do? Sometimes we have to add, sometimes we have to multiply, and sometimes we have to divide, right? So how do we calculate the uncertainty? How do we calculate uncertainty if two quantities are added together? Okay. So now, meaning if I want to do x plus y, right? So like so, so we say the added quantity z equals x plus y, okay? And if I want to add this thing, so now what is my delta z? What will be the uncertainty in my z measurements? So what we know, x plus y, we can write down as x plus delta x plus minus, forward here minus here, x plus minus delta x plus y plus minus delta y, right? So now what we have here, so what you can say here, x plus minus delta x plus y plus minus delta y, or I can say x plus y plus minus delta x plus delta y. Can I write down this one, or is it like a one-step jump? Okay, let me break it down by one then. So here, delta x
Oh my
plus
God.
minus, what happened? Mia, what happened?
The lady next to me, like, was taking her time.
Sorry? Hello?
Are you on? Mm-mm.
Mia, are you all right? Okay. So plus minus delta y, right? So now you can simplify this expression as, so now plus minus, so I can take this plus minus common, so which will be basically delta y, right? So now what is this this x plus y? What is this x plus y? This x plus y is my z, right? So that means this is z plus minus, now what is this quantity? This is delta z. So that implies my delta z is equals to plus minus delta x plus delta y. Make sense? That's my uncertainty. Now, as you look at this expression very carefully, so whenever we're measuring this uncertainty and the value of the addition of two variables, we will add the uncertainty of each quantity. So there is no minus here, it is plus. So this uncertainty is always added. Make sense? Make sense? Okay, so chat. I need to see my chat. Okay. I need to put my chat in the screen so that I can see you guys all. Okay. Okay. So yeah, Tiffany, if it's not working, so maybe like, you can also watch the recorded later, but hopefully it will be a good connection soon. So these are the first conditions when we are adding two numbers, right? So now in the second situation, if I do x times y, right? So if my z value is x times y, so how we gonna calculate this one, right? And how we're gonna calculate the uncertainties. So what we know now from this one, what we can do, what is x? So x plus minus delta x times y plus minus delta y, right? So now what we're gonna do, we're gonna do the distribute property. So then x times y plus minus x times delta y plus minus delta x times y plus minus delta x and delta y, right? Now, if you look at this quantity, so this is basically, it will be more like a plus. So now if you look at this quantity here, so what do we see here? So this quantity here, uh, delta x times delta y. So this is like a smaller number. So if we are multiplying 0.2 times 0.2, what is going to be? 0.04, right? It will be even smaller, right? So that means this number will be really small compared to this number and this number. So that way we can disregard this number and we can say this is negligible. So we can neglect because it does not make any much significance in our calculations. Okay, so that means I can write down this expression as xy plus minus, again if I take the bracket common out, then plus y times delta x. Okay, so that means my delta z in this condition is x delta y plus y delta x. Make sense? So this is my uncertainties. Now again, to make this like look very pretty and pretty and simple. So what we can also do is like if we divide both sides by z, right? So on this one, delta z divided by z, and then what is x times delta y? What is z? X times y plus y delta x, x times y. So now what do I have here? I can get rid of this x, I can get rid of this y, and then delta z over z is basically delta x over x plus delta y over y. Or in other term, we can also say delta z is z times delta x over x plus delta y over y. If you calculate some value of your product, right? So you can calculate delta z in two different ways. Either you can say this, Or you can say my delta z, whatever this thing is, whatever the value we calculate, x times y times uncertainty on the x value divided by the value of x plus uncertainty on the y divided by the value of y. Make sense? Following here, right? So now this product rule was for, this was for when z is simply x times y. So remember here, the x times y has like a power, simply power of 1. So now if I have my z such that x has some power of m and y has some power of n, right? So now if we have this, so now we can derive this one, but there is no need to derive. So based on this expression, what we have here, right? So what we can say, delta z over z in this condition will be whatever this power here, so they come out. So we take the absolute value of this one, delta x over x plus absolute value of n, delta y over y. So this is how we calculate the uncertainties, okay? So that there are 3 different conditions. So we will use this method to do our uncertainty in our calculations. For example, now since we did this, for an example, right? If we want to calculate an area of a circle, right? So what we know, circle, area of a circle with radius 2 centimeter. So what that will be? A equals pi r square. So now you can think this r square, pi r square, as like a term where z equals to x times y, or you can just say z equals to r x to the power m. You can think in both ways. So both will give you the same result. But now only thing different here is we have this multiplication of factor pi constant. So that will always remain, right? So now in these conditions, my delta A will be, if I use this rule, right? So delta A over A equals, so pi as it is here, right? And now what happens? So 2 will come out, delta R over R. So this will be my uncertainty. Okay. Or if we go use this, or if you use this, delta A will be what is my area times what is my delta x over x. So again, same power. So like again, we can derive this one. Okay. So since this is simple, so A equals to pi r square, or I can say this is pi r times r, right? And if I say there's an uncertainty in radius r equals to 2 centimeter, and uncertainty in r is delta or delta r equals 0.1 centimeter, suppose, right? So what I can do in this one, pi r plus delta r times r plus delta r, right? So pi remains as it is, r times r square, r times delta r times delta r plus delta r times r plus delta r times delta r. Now again, since this is small number, we can neglect this one, all right? And then if you see pi r square plus 2r delta r, right? So I didn't, okay, yeah, right? So now this is my area. So now A is what? So I have pi r square plus 2 pi R delta R. And what is this quantity my? This is the area itself. And what is this? This quantity is my, I forgot to do plus minus here, right? Plus minus, this is my delta A. This is how you get the delta A, which is same as this quantity here. Is same as this quantity here. So there is no pi here. Okay. Yeah. Okay. So this is how we're gonna calculate our error. Make sense? So we will use this method to this calculate the error, because like if you calculate your measurement, and this is called what you call like how you propagate an error, or like how the error in your measurements, how this error in your measurement will translate into the other calculations. Okay. Okay. Where is the mouse? Okay, here's the mouse. Okay. Okay, that's okay. Imagine. Make sense until here? Okay. So in today's lab, we will be using this method to do our uncertainties as well. Okay. So you will get to use this one and now do the calculations. It will be much more clear once we started doing that one in the class. And the next topic is vectors and vector addition. So if you have taken the high school physics earlier, so you might have like heard this word like a vector, right? Uh, right? How many of you have heard this word vector? Okay. So the vector, so again, so if someone who has not heard about it, so now any physical quantity that we measure, it has two quantities. One is called like scalar quantity and another is called vector quantity. And scalar quantity has just the magnitude, meaning the value, the number itself within units. But the vector has the magnitude with the units and it also has a direction. Okay. So meaning, so if you want to walk, right? So if you want to go out for a walk, so you get out of your house, get out of your door, then which direction that you want to go, left or right? Now you choose a direction to go to the right, say like 2 miles to the right. So the to the right is the direction, 2 miles is the magnitude, right? And that is like, oh, I went out of my house to the right for 2 miles for a walk, right? And then now someone say like, okay, how many miles did you walk today? Today I walked 2 miles, right? So that means in that condition, you are only calling the magnitude. So those are scalar quantity, the magnitude. So now what differentiates and how we differentiate? Okay, now I said the same 2 miles are vector and same 2 miles are scalar. But what differentiates between the vector and scalar? So like if we are taking a mass, if you are measuring a mass of an object, so 10 kilogram of mass is a scalar quantity. Okay, so why? So if you take this 10 kilogram of mass and measure in Earth or measure in a moon or measure in a Mars, it will be 10 kilogram. So meaning if you have like two pencil, see the two pencil in the Earth, two pencil in the moon, two pencil in the Mars, it will still be two, right? Same thing, the mass. It's a physical quantity, mass. Now, when you measure the weight, weight is mass times the gravity, right? So now this weight keeps on changing. from place to place where you measure, right? Because the direction of the force that is pulling downward changes based on where you measure, from Earth to Moon to Mars. The gravity changes. So that will change the value, magnitude, weight itself. And that is the direction. And what direction? Towards the center of the Earth. There's a force acting on, right? And that's a vector quantity. Similarly, so distance and displacement, right? So distance is a scalar quantity and displacement is a vector quantity. So what does that mean? So if you are traveling from point A to point B, so if you want to go from point A to point B, how many ways you can go from point A to point B in this particular diagram? Two? Any other thoughts? How many different ways you can go from point A to point B, right? So now I will say, yes, I can go point A to point B, point A to point B, point A to point B, point A to point B. How many different ways I can go from point A to point B now? Infinite. So there is no only one direction. So there's like a multiple infinite ways that I can go, right? So now the path that I follow here, so this is my distance. And the displacement is the shortest distance from A to B, the perpendicular distance. So that's a displacement from A to B. So going from right to, so from left to right, that is my displacement from A to B. And distance is whatever the distance, like a kilometer, meter that you travel, that's a distance, right? And distance depends on its path, which path do you take. But displacement is always same from initial point to the final point. This A is the initial point and B is the final point, right? So that's the difference between the scalar and a vector quantity. Now here in this case, the distance is a scalar quantity, but displacement is a vector quantity because the displacement is a direction from A to B. So distance, you can say like, you can go from this here or uh, go here, right? So it doesn't care about going from A to B or B to A. So distance does not care. So distance is always positive. So we'll talk about this a little bit more. But now, since we say the vector, so vector, as you see here, so vector we represent with a direction. So I'm going from starting to initial to end. So that means this vector are generally represented by an arrow, which has initial starting point and a final point. So this is initial point, and this arrowhead is your final point. Okay. So now, as I said, so we can go from starting point to initial point, right? So there are multiple different ways you can go. So like all these vectors, right? And then if you want to notate a vector, so if I say this vector, right, has this vector from here to here, the magnitude of this length is say, suppose A, right? So this magnitude of this vector going from here to here, this length is A. So in that conditions, so I can write down this vector as in terms of a bold A or A with an arrow, right? And then same thing we can also write down with magnitude A and some with a unit vector. So three different ways you can write down. One with the letter, whatever the magnitude with a bold A, or A with an arrow on arrowhead on the top, or we can have the magnitude and write on the unit vector. So now this gives you the magnitude and this gives you the direction. Okay. So now that comes the velocity. The velocity is a vector quantity, while as speed is a scalar quantity. So velocity, so it points from initial point to final point directly, right? The speed is like, the when you're driving your car, the number that you see in your car is called speedometer because it says it's a speed. Because constantly you are changing your direction. You are not going into like one particular direction when you're driving a car in a road, right? It goes along the direction of the road, right? So that's the speed because it continuously changes the direction, right? But the magnitude is remaining constant. So that's why it's a speed, not the velocity. When you say velocity, then you have to have the magnitude, which is the speed, constant, like a 50 miles per hour, and also your direction needs to be constant, fixed. Okay? Make sense? So now, since I said that, so in general, so we can represent a vector in any space, right? So suppose we have this coordinate system. Now, okay. So we have this x and a y is an origin, right? So this is where coordinate system. So now if we have a vector, this vector going in these directions, okay? Now I have, and then I have another vector here. So now this is like, say, this is my vector A, and this is my vector B, right? So now if you look at these two vectors, are they equal? Yes, they are equal. So what does that mean? It only needs to, if the magnitude and the direction pointing the direction is the same, then those two vectors are same. It does not need to be overlapping on top of each other. So they are the same vector, right? So meaning if I will take this vector B and then I drag and I bring it up here, so they completely overlap, right? So they are like same vectors, okay? But now, if I will take this vector, and I flip this, let me see, duplicate, and I take this vector, and then if I flip it, right? Let me write down this one, not the B, C, right? So now vector C. So now if I bring this vector C on top of this vector A, and let's make this magnitude also like similar of same size. Almost the same size, right? Okay. Okay. Yes. Okay. So now if I bring these two vectors, so now as we said, vector A is equal to vector B. So how about vector A with vector C? Are they equal? No. So they are equal in magnitude, but they are not equal. In direction, they are not equal. So for any vector to be equal, so they need to have like both magnitude and direction to be same. So that means vector A is equals to negative vector C. So they are equal but opposite. So that means we cannot say C vector is same as A vector. And then these vectors in space can be anywhere. If they have like equal magnitude and the same direction, no matter where in the coordinate system you put, they will be a same vector. Because as I mentioned earlier, I can bring this vector and put it down here, so they will exactly overlap on top of each other, right? So that's why vector A and vector B, so they are a same vector, right? So now let's say you are walking a path from this point to this point. You went in this direction. You decided to move from here to there, A, and then you stopped here for a while, and then you decided to change your path, and you moved and you walked in this direction, right? So direction and with that particular stretch of length, okay, in same directions. So now, so what is my total vector? So now if you want to count the distance that you walked, so then your distance would be from this point, your distance would be going from this point to this point plus from this point to this point. That will be your distance, right? But now when you calculate the vector, so addition of this vector, what will be my final vector, right? So now the final vector would be as if from, like, let's say this is point P, this is Q, this is point R, okay? So now I need to go from point P to point R. Do I have to go through point Q to go to point R? Not necessary. So I can go from point P to point R directly using a very shortcut method. So this direct distance. Now this quantity going from P to R, this straight line, is the addition of these two vectors. So because from here you go one this distance and from here you went distance. So remember here, so this plus this is this in a vector notation. Now if I say this is my resultant vector C, this resultant vector C is addition of vector A plus addition of vector B, okay? But now when you see the magnitude, so the magnitude of C will not be equal to the magnitude of A plus magnitude of B. Makes sense? It's not simple algebraic addition. It's a vector additions. And how do we do that? How do we calculate this vector additions, right? So until now, you guys are following here? Any questions before things get more confusing? Okay. Everyone is good then. No questions here, right? So now to add these vectors, so now this is like in terms of like a walking path that we say, right? So, but in general, in our regular vector additions, we might not always have like same that kind of situations, right? So I can the same vector, this A, right? And then this vector B is here, suppose, right? I have two vector. This is vector B, so this is vector A, right? So now what will be the addition of these two vectors in this case? What will be the addition of these two vectors? Okay. Now, to add these two vectors, what I can do, as I said, I can bring this vector B on top, right? So now this vector B and this vector B, they are the same thing, right? So remember, in a vector, it can be anywhere in this space. It just needs to have the same magnitude and the same direction. So now this vector B and this vector B, they are the same thing, right? Maybe I want to make it like a different color here. Dun, 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 dun. Okay. And then style. Okay. Right. So these two vectors are same vectors, even though they are in a different place in this space. Those two vectors are same. Now, if you look at these conditions, addition of this A vector plus B vector, now this looks same as this vector plus this vector, right? Makes sense? So that means I can get my resultant vector from this point joining to the final position. Let me go do a different color. In this condition, this will be my final vector C, which will be the addition of these two vectors. Make sense? Make sense? And also know, to further understand this one, I can say again break it down into more uh, easy way. So suppose I have these two vectors, vector A and then the vector A and this vector B, right? So now to add this vector, what I can do, I can create a rectangle, a parallelogram, sorry, not the rectangle, a parallelogram. You know what, I'll just copy this one. That'll be much more appropriate. Duplicate, bring it down here. And then here is this one. Done. I don't need to erase this one. I'll bring it here, right? So I can draw this parallelogram, right? So I can just draw these vectors. So this one parallel to this one parallel to this one. Now it became a parallelogram. So where did we start from? We started from this point. Now, if we draw a diagonal of this parallelogram, right? If I will draw a diagonal of this parallelogram, this is my resultant vector C. Make sense? Make sense? Now, if you see this more critically, first vector starts from a point, and the second vector starts from the final position of the first vector and goes on. Make sense? First vector is starting from the initial point, and then second vector will start from the final position of the initial first vector and goes on. And then you will just join the initial position of the first vector and the final position of the second vector. And that is my direction of the addition of the final vector. It is same as you are walking on a floor. So you went right 2 step, and then you moved uh, front 2 step, right? And then what did you? You moved 2 step to the right, 2 step to the right, and then 2 step to the front, right? You end up this point here. Now to get this point, what you can also do, you can directly move from here to there, right? Which is the same results as you are going from here to there and there to there, right? So this is what is the addition of the resultant vector. You can understand that way. Make sense? Yes? Okay. I'm trying to go a little bit slower because this vector, this concept is like really important. And once you get this concept, slowly I will pick up the speed. Okay. So now, if I have a vector, this vector A in this direction, and then another vector B, my resultant vector will be, what will be my resultant vector in these conditions? A plus B, it will be simple addition, right? Because they both are along the same line. So my resultant vector will be this length, this C, which is equals to A plus B, right? So now, in first case, I have this vector A of this length, right? And then I have a vector B in this length, right? So what will be my vector in these conditions? If you can annotate it, you can go ahead and annotate it as well. Okay. So yes, A plus uh, B is already a negative. So yeah, I understand what you're trying to say there. Yes. So it is basically the resultant vector will be this C, which is A plus B, right? So you are subtracting the length of a B on A, right? And this is very easy, right? Because this is all like one straight line, right? So now if you have like multiple vectors, right? Suppose we have this vector A in downward direction and then vector B in this direction, and we have like another vector C in this direction. Now, how do we add these vectors? What will be the addition of all these three vectors, right? So now what we can do, bring a little bit down here, right? And then duplicate, and then I'll bring it down here. So now to add these vectors, what we can do, the simple way is like, so I can just bring this down here, right? And then I'll just bring this vector down here, right? So what did I make? I made these vectors, rather than all three vectors starting from the same initial point, I start from this point, I went here, and my second vector started from this point, and my third vector started from my final point of this vector B, right? And now just looking at this one, my final vector is from the initial point to the final point. This is my resultant vector. But again, to see that one, what you can also do is like, okay, so this is my vector A, this is my vector B. So if I add these two vectors, my resultant vector in these conditions would be going from this length to this length, right? So now let's say this is my vector D, right? So now what we have? One vector D plus this vector C. So now we need to add this vector and this vector. So again, if we add these two vectors, then my resultant vector will be going from this point to this point. So which is basically what? Vector D plus vector C. So this is my resultant vector. Okay. So now what is D? So D is nothing. D is my vector A plus vector B. So that means my this R vector is vector A plus vector B plus vector C. Make sense? Okay. Hmm. Let's see what else should I tell you guys? And then components, okay. So now, after we do these vectors, right? So this is like one graphically, we can do this one, right? And then the next topic that we can talk about is components of a vector. Over there, let me see if I can show you this one. So let me share my computer screen. Huh? Okay, you guys can see my screen, right? And this is a very nice tool for you guys to practice. I made this one. Right? Go to this tool, right? And so you'll open up this one. So what you can do here, so like if you do new problem, so it will give you new problem. Now what you need to do, so you need to add this vector P and vector Q, right? So what will be the addition of this vector P and Q, right? So now drag this red vector and then say where it's gonna be, right? So now how are we gonna add these things? So now to add this one, what you can see here, this P vector is 3 units to the right and 4 units to the top, right? So this is my P vector. And now my this Q vector is like what? So how many, 2 units to the left and 4 units to the right, up. So that means from this point, I can go 4 units up, 1, 2, 3, 4, and 2 units to the left, 1 and 2. So this is where I'm gonna end up. So that means here. So this will be my resultant vector. So P and Q addition of these two vectors. Make sense? Make sense? So now if you do submit, then you say like correct. So number of correct answer 1. Right? And then you say number 2. So now it again gives you a random vector P and Q, right? So P is 3 step up, right? So from here, so you go 1, 2, and 3. So this will be your final vector. So that means this will be your final vector and submit. This is correct. New problems, now here. So this is like a practice. So it will give you a good practice to do these vector additions. Make sense? Try using this one and then it will be much more easy and do this vector additions. You guys, were you guys able to open this link? Okay. Okay. So now this one is just an addition, and also it will give you the coordinates here. What is my A? What is my B? Final point. So it will give you a coordinate and you can see, right? Okay. So I wanted to share you this. So save this link and then you can try next time. So to feel more comfortable about these vectors. Okay. And now coming back to this components of a vector. Okay. So what do you mean by components? Right? So components meaning, so it has X and Y values. Okay. So components are such that we can represent any vector in terms of X and Y. Okay. So now here, now comes the use of a trigonometry. Okay. So now if we have a right angle triangle, right angle triangle, yes, the right angle triangle. Oh, no. Yeah. Right, so this is a right angle triangle. So now this is my angle theta of interest, right? And this side is called hypotenuse. And this side is the opposite of this angle. So that's why it is called opposite. And this side sometimes in some books or like from sometimes I might say perpendicular because from this point I'm drawing a perpendicular down to this base. Okay. So sometimes don't get confused if I say this is perpendicular. Okay. And this one is the side which is right next to this angle theta, which is adjacent to this angle theta, right? So now this is called adjacent, right? And then don't get confused sometimes if I say base. Okay. So I might say perpendiculars or I might say base. So again, perpendicular means always opposite to the angle of interest. So based on what is your subject of interest of angle. Okay. And little bit of revision of a trigonometry here. So sine theta is basically opposite side over adjacent side, right? And cos theta is basically adjacent side. Oh, I did. Oh my goodness. Now this one. I missed it. I was like totally hypotenuse here. Right? And then cos theta is adjacent side over hypotenuse. Right? And then tan theta is opposite side over adjacent side. So which basically means sine theta over cos theta. Okay. So this is a little bit trigonometry. And what we also know, so sine square theta plus cos square theta is equals to 1. So these are another trigonometric function. So which we will be using a lot, very frequently. So now, how did this sine square theta plus cos square theta equals to 1? Can anyone prove? Do you guys know? Do you guys remember? Let's say this way. Do you guys remember? Okay. Well, I just remember that I need to take your attendance as well. Yes, a square plus b square equals to c square. What is that rule called? What's the name of for that one? Pythagorean theorem, right? Pythagorean theorem. Okay. So now we can easily prove this one. So let's see if it is same thing or not. So now here, opposite side, I'll just write down shortcut here, over hypotenuse square plus this is what is adjacent side square over hypotenuse square equals 1. Now, if you take this, the least common factor multiplier is what? Opposite square plus adjacent square equals 1. So this is basically opposite square plus adjacent square is equals hypotenuse square, which is same as a square plus b square equals c square. And sometimes I might also write down h square equals p square plus b square. Okay, so I might so it's the same thing here. So I'm just like saying, so based on sometimes I might say h square equals to p square plus b square. Okay, so same thing. So this is a Pythagorean theorem. So now this expression here is nothing new. It's just a Pythagorean theorem, but writing in terms of a trigonometric function. Make sense? Okay. Uh, let's do a check-in for this class. And then I'm giving you guys a code to check in for the class. Go here, go to this attendance and go ahead and check in yourself. And I'll give you guys a 5 minutes of break before we continue. Sounds right? Welcome back. Sorry guys, here. Guys here. Okay, good. So now, as you see in this right angle triangle, right? So this is my, so suppose this is my x-axis, and then this is my y-axis. And let's make this vector color a bit different, right? And then I'll make this one also different, right? So we have this vector here, yeah, in this vector, which is, this vector is, let's say, A. Let me use a different color. So this is my vector A, right? So now, so this vector, I can project this vector into the x-axis and the y-axis. What do you mean by project? So what I'm going to do, I'm going to draw a perpendicular line, and then okay, here, okay. Yeah. So now from this one, I'm going to draw a perpendicular line to the x-axis. Okay. So now once I draw this perpendicular line, so this is my projection. So that means how much of this vector is along the x-axis. And this is called AX, right? And now similarly, if I will draw another perpendicular line from this vector A to y-axis. From here, if I draw another perpendicular line, right? So this is perpendicular and this is also perpendicular, right? So in that conditions, this is okay. Okay. So this is my, this is another color. This is okay. So this is my another component AY. This is my projection AY. So this AY will be same as this length, which is also AY. This and this length will be same as this length, so which is AX. Okay, so my thing right? So make sense? And what are these AX and AY are called? And they are called the components. So this AX and AY are the components of vector A in X direction and Y direction. Make sense? Right? So now, looking at earlier vector additions, this vector plus this vector will give me this vector A, right? Can you say this vector plus this vector will give me this vector A, right? So that means I can write down, I like my blue ink, I don't know why. So this A vector I can write down as a sum of AX plus AY. Make sense? So what does this mean? Vector A is a sum of component vectors, right? Again, this is a vector addition, not the algebraic addition. This is a vector addition. Make sense? Yes, no, maybe. Right? So now this is what? This is a right angle triangle, right? What is AX according to right angle triangle? What is AX? Or like, let's say, if you don't remember exactly what is AX, okay, right? So that means I can write down sine, if I say this angle is theta, this vector A is making an angle theta, right? Sine theta is what? AY over A, and similarly, cos theta is AX over A, right? So that means I can write down my AY as A sine theta and AX as A cos theta. Make sense? Right? So now, according to Pythagorean theorem, so this vector A square is equals to A square equals to AX square plus AY square, right? So if I want to find the magnitude of a vector A, right? So this is square is equals AX square plus AY square, which is A square plus B square equals C square, right? So what does that tell me? So again, I don't have to write this magnitude all the time. If I just write A, not a bold A and without an arrow, it's a magnitude. And it's basically this is equals AX square plus AY square. So that means I can write down my vector in terms of a component form so that it is square root of X component is square plus Y component is square. And that will give me the magnitude. Make sense? Right? So that means of any vector, if I know the X component, if I know my Y component, I can calculate my vector A given, right? X component and Y component. Now, if I know my X component and Y component, I can calculate my vector A. So now, can I calculate what is the angle? Let's see. Again, from trigonometric function, what do we know? Tan theta is what? Opposite over adjacent, right? And this is also equals to what? AY over AX, right? Opposite is AY and adjacent is AX. So tan theta is AY over AX. So that means my angle theta will be tan inverse AY over AX, right? Or theta will be tan, yeah. So if you are given the yes, right? Make sense? So this is how we will calculate the angle of a vector. So that means if I want to find the direction, so you take the tan inverse of the ratio of y component of the vector divided by the x component of the vector. And this will give you the direction. Direction of a vector. And this will give you the magnitude of a vector. Okay. So again, whenever you are asked to find what is the vector, so whenever you are asked a vector, then you have to find the magnitude and a direction. You cannot just do the magnitude. You cannot just calculate this value and say, I'm done. You have to calculate this one. Okay? So you need to calculate both magnitude and direction whenever you have to calculate the vector. Suppose if you are given what is the amount of force, then so you say force is 5 Newton at an angle of this with respect to x-axis, whatever. So you have to find the angle as well. Make sense? Whenever you are calculating a vector quantity. Make sense? Yes, no, maybe. Okay. Mm, okay. So I will go this further addition details like of these two vectors when I will go into this two-dimensional motions. Okay. So for addition of this one, I'll cover when I will be doing two-dimensional motions. Let me see what do I have. But, okay. So right now we'll just about the vectors additions. I'll just stop here about the vectors, but I will continue on this one uh, in another topic when we are going to talk about the inner plane. Okay, but before we switch gear, since we are only doing this what vectors and one directions and all those things. So now we're gonna I will switch my gear to a motion chapter 2. Motion along a straight line. Okay. So so it is basically meaning motion along a straight line, meaning it is also known as one-dimensional kinematics. Okay. So it's the same thing. Motion along a straight line or one dimension. One dimension meaning it is only moving in a one direction, unidirection. It is not moving from like left and right. It is only moving either left, it is only moving like right, it is only moving up, or it is only moving down. Make sense? Okay. So now I'll just give you like a little bit of a hint how this physics chapters are defined, how this physics things is done, right, in a chapter. So first, the very first thing that we learn in a physics is what did we learn? The measurements, numbers. And then we associate that numbers with the units, right? And then with number and units, and then we associated that with the directions, right? So every time we are adding one parameter into that one, right? And uh, once we, all this will give you what? The vector, the directions, and everything will give you the position of an object, right? Which is the coordinates. Now, once we know the position, the coordinates, right? In a real life, that object is not stationary all the time. It is moving, right? So then, so after position, we say how this object is moving. We'll evolve from that, from coordinates. So now, until now, we have seen an object and that object is moving, right? And then we comes into terms called velocity, right? How the position is changing. First is like position is changing, and then how fast it is changing its position. And that gives you a velocity, right? And then we'll again further go and say how this velocity itself is changing, right? So when you're driving a car, right, you pick up, right? The first like you hit the gas and you pick up, right? So what happens at that point? And then finally, once you are in like a freeway, unless you are doing like a road race, but otherwise, if there's like a speed is like a 70 miles per hour, So what you try to stay 70 miles per hour. But before hitting that 70 miles per hour or 60 miles per hour, so your car will be changing its velocity. Like as you see in your odometer, so it goes from like a zero and then it keeps on changing. And then at certain, and once you're in a freeway, like, if you are 60 or 70 miles per hour, your speedometer will keep on staying at the 60. But before that, what is happening? The speed is changing, right? And then what is the rate at which your speedometer, like, the speed is changing, that is called acceleration, right? So that means now we know the position, the distance, and then now we know the velocity, and now we know the accelerations, right? And then again, until now here, we haven't talked about how big the size of the object is, how heavy, how small, nothing. We didn't say anything about it. So that's what the one-dimension kinematics is. In one-dimension kinematics or motion along a straight line, in this problem, we will not talk about mass, how big, small, right? It only cares about the motion, how fast is moving, how slow is moving. And then and this is only in one dimension. And then slowly we will evolve into from going from one dimension to the two dimension, right? And then so from two dimension we can go to three dimension, but we'll keep it short, and then we are only doing up to two dimension. We are not doing the three dimension. And after that, so now the motion is done, then we will involve the quantity called like mass, how big, how small, and then comes the Newton's law. And that's how this whole chapter is being progressed. Make sense? So each chapter is connected to another one. So each chapter is built based on another chapter. Make sense? Yes? No? Okay. So when you are doing with the one dimension kinematics or like motion along a straight line, here we don't have to worry about the mass, the object, anything, right? So what we only deal with is what is the speed, what is the acceleration, what's the distance, what's the displacement covered, right? So those are only things we will be talking about in this chapter 2, which is motion along a straight line. Okay. So now the term comes like a displacement, right? Or I can use my presentation. Right. I can also use my presentation here. And then I can share my screen with you guys. Where is my mouse? Share my chapter. Share. And then you guys can see my slides, right? With the white slide with this written kinematics. Okay. So again, what is the kinematics? It is a description of motion of an object without considering the cause of the motion. So again, in this case, we even don't investigate on what is the cause that is causing a motion. We don't even think about that. Okay. So it doesn't really matter. We are not looking for any cause of a motion as well. And in kinematics, we do not consider the mass or size of the moving object as well, to keep it simple. And also, in kinematics, all moving bodies, irrespective of their geometric sizes. So geometric size means like a rectangular, circular, uh, how big, how small, it doesn't really matter. Everything here in this kinematics, in this motion along a straight line, is considered a point particle, a point mass. If you are saying a big truck or a car, it doesn't really matter. So they are just a point mass. Make sense? So that's what the one-dimensional kinematics does. So basically, we are trying to work on a very simplified model where we can describe the motion of an object. It's a very simplified version. Okay. So now, so anything we can define with the positions, right? And to define the positions, we have what? The x, y, and z coordinates, right? We have like 3 different coordinates, x, y, and z, right? And then in these 3 coordinates, so x coordinates is represented by x1. Let's say there's an x1, there's an y1, and there's a z1. And the intersecting of all this is like a O, with the origin. And remember this x, y, and z, they are all perpendicular to each other. Okay. So now if we are drawing a line, so this intersecting point of x and then z, so this gives a point Q. Now if that point is Q has a coordinate x1, in the y coordinate is 0, in the z coordinate it is z1, right? And now if we will draw a perpendicular line from this Q parallel to the y-axis and perpendicular to this xz plane, and then if we draw another perpendicular line from this point P to the y-axis, this point P has a coordinate x1, y1, and z1, right? So these are 3 dimensions. So in space, it can represent by the 3 different coordinates. But what we are interested today, so we are interested in this chapter, we are only interested about the 1-dimension motion, right? And this object, point P, could be stationary or it could be moving. It is based on the frame of reference. What do you mean by frame of reference? It depends who is looking at it. Okay, from where the person is looking at it, right? So in this case now, so like there are like how many frame of reference do we have here? We have 3 different frame of reference here. A person in a bike, a person in an airplane, a person in a house, right? There are 3 different frame of reference. So a person who is in the house, in the land sitting, right? They will see the motorcycle is moving forward, airplane is moving with a higher speed forward in the sky. But for the same time, a person from the motorcycle will see the house and the trees are moving backward with certain speed. And from the airplane, they will see everything is moving backward with some higher speed, right? So now, again, if you zoom in inside the airplane, so there could be a person, right? So there are like 4 different rows of seats. And now, since now the person inside the airplane seems themselves in completely relaxed position, sitting there. They are not moving at all. So they are moving and sitting in the same place, right? So in that conditions, all these persons are not moving. But with respect to the surroundings, like surrounding means outside of the airplane, with respect to the clouds, with respect to the earth, so they are moving. But with respect to the airplane itself, which is their frame of reference, right? From their frame of reference, so they are sitting. So meaning with respect to the chair, they are sitting in the chair. But now if this person moves from this chair and goes backward, so now this person moved in that frame of reference with a certain distance. And now since he moved, what is the distance that they move? This person moved a distance of 4 meters, right? So he moved a 4 meter a distance. Now, what is his displacement? He moved negative 4 meter. So what does that mean? Negative 4 meter means from his position, he moved 4 meter backward. Make sense? Make sense? So now to find the displacement, here it is written delta x is equals to xf minus x naught. All right. What is xf? xf is the final position and f naught is what? Is the initial position. Okay. xf is the final position, x naught is the initial position. And then this is, and then whenever you want to find this displacement, you always subtract from final to the initial. Okay. Now the state of rest or motion, right? The object or particle is not changing with respect to its surrounding, then it's called we already know it's like a rest. But if it is moving, then it is in the state of motion, right? So like here, a person is living in a chair and in his bed. So like, from night to day, the person is still in the bed from the night to the morning. He didn't change his position. So basically it's a rest. So again here, so playing a baseball with respect to the surrounding the trees, so the ball and the bat, they both are in a motion, right? So there's an object in a motion. Now again, this vector, this object, the ball, with respect to this origin of the coordinate system, right? It is started at some point, but this the direct distance from the origin to the ball is the direct displacement of an object, right? And so now, so that's why, so whenever we say the rest or motion, so there is no way that we can say an object is completely at rest or completely in motion. So it just depends upon what frame of reference you're looking at. So when we say we are in a rest, sitting in a chair right now, we might be in a rest, but we are not in a rest based on if someone is looking from outer space. What do they see us? Spinning with respect to the Earth and moving along the solar system, right? So in that conditions, we are not in a rest, even though we are doing nothing, sitting in a chair, but still moving. So that this state of rest or motion is based on the frame of reference, where you are looking from. Make sense? Make sense? Okay. Now then comes the one-dimension kinematics or one-dimension motion, right? Again, here that's what we had. Like earlier, I mentioned this: any position in this space can be represented by three different coordinate systems, x, y, and z, making a perpendicular line, right? So from there, there's my x1, and from Q, if we draw perpendicular onto the z-axis, the section O to z1 is a z1 coordinate. Now, one-dimensional motion, this is a Cartesian coordinate system. So in one-dimensional motion, what you can do, so we make all other coordinates y and z 0. So we are only taking x. And again, it doesn't need to be on the x only. It could be only along the y. It could be only along the z. Okay. For simplicity, here is considered along the x-axis, right? So now, if we move this object point P to another point Q by a distance of delta x to a coordinate x2, right? So this is a motion in one dimension. And then this change in position delta x is again final minus initial. So what is my final? Final is my x2, initial is my x1. And here we don't have to worry about y and z because y and z is 0. But in second conditions, we don't really have to move, only consider x point P along the x-axis. It could be up in this space, but what if we don't change the coordinate of y and z, then still it is moving in a one-dimensional motion. Make sense? So here, only the x coordinate changed, not y, not z. If I'm going from point P to P prime or going from point Q to Q prime, only the parameter that has been changed is the x. Rest of them are remaining the same. And this kind of motion is a one-dimensional motion. Okay? So we already talked about these vectors and scalar. So how we write down this vector, displacement velocity, right? From point A to point B. And again, we can go in a different path. So that's a different path is like distance. We already talked about it. And displacement is a direct point from point A to point B. And this displacement is measured in a unit meter, and same thing with the distance also in a meter. Okay, and displacement is not a commutative. What does that mean? Commutative means, what does it mean by commutative? Anyone? Anyone? Yes, no, maybe. Okay. Yes, order matters. I don't understand what you mean by can change. So what does it mean that? So A minus B is not same as B minus A, right? So it does matter in the order, how you put the order. So that means here, so delta X BA is not same as delta X AB. So they are equal but in opposite. So that's why here there's a negative sign here, right? So delta XBA and delta XAB, they are not the same thing. Okay. So meaning final position minus initial position is not same as initial position minus final position. So then you will get a negative sign, right? So that's why in a vector, in a displacement, the order matters. That's what you mean by it's not commutative. But in case of scalar quantity, and scalar quantity has no plus or minus sign, and in case of distance and speed, right? So it could be A to B, so no, or for like going a multiple path. So that's a distance, right? And distance is always a positive quantity. Distance is always a positive quantity, while displacement can be a zero. But zero mean in the sense that if you move an object, right, the displacement could end up being zero, but there could be a positive value of distance. Distance is never negative. Displacement can be zero or displacement could be negative, but distance, if the object moves, distance is never zero and distance is never negative. We'll talk about that one. And distance is commutative. So like x minus xb minus xa is same as xa minus xb. So here the order does not matter, right? So now how come the distance is not zero, but the displacement could be zero? For an example here, we have this ball, and if this ball goes in a circular loop, right? If it goes in a circular loop, then what happened? So initial position and the final position is the same, right? So now here, the displacement is zero. Where you started, you ended up being at the same position. So displacement is zero. But the distance is what? It went through the circular path. You go and add this path length, and that's the distance. So how much distance did it move? 2 pi r. That's the circumference. Displacement is zero. Make sense? For displacement, only the initial and final position matters, not the path. But in case of a distance, it does matter the path, what path you are taking in a distance. But in displacement, it doesn't matter because there's only one path. That's the shortest path, right? From point A to point B, and the what direction. The same thing here. So let's say the positive, that's why it's a negative displacement. But in the case of distance, it is only thing. So here's like a difference, like, I'll just go ahead and populate this one. So there's a difference between the distance and a displacement, right? So here, so distance is a scalar quantity and has magnitude, no direction. Distance is positive quantity and covered in a, so it could be, it is never zero, that's as I mentioned, and it is never negative, it is commutative, right? And this distance covered by a moving particle never decreases with time, it always increases. But displacement could be negative. Okay. And the magnitude of the displacement could be less than equal to distance. But distance is always greater than or equal to displacement. Okay. The magnitude of distance could be always greater than or equal to displacement. And displacement is the what? The minimum distance between point A to point B. So you can think about what the shortest distance or perpendicular distance from point A to point B. That's the displacement. That's the magnitude of displacement. Okay. Why did I go back? And same with the speed and velocity. So the speed is a vector quantity, right? It's a distance over time, right? And speed is either positive or zero, but never negative. And speed is measure of a particle, how fast or slow the particle is moving. Zero speed of a particle or a body is said to be in a rest. If the particle is not moving at all, it's at the rest. So, but in case of a and dimensionally, again, we said it's a length over time, L over T, right? And the uniform speed, meaning its magnitude is same, meaning the number of distance travel for equal interval of time. If it travels equal distance in equal interval of time, meaning if every 5 minutes you are traveling a distance of like, uh, let me see, what would be like 100 meter, right? Every 5 minutes you are moving a distance of 100 meter, or you are walking a distance of like 100 meter. So your speed is uniform, right? Makes sense? But it is not necessarily that your direction is same. Okay. So and then since this speed and time, speed over time is speed is distance travel over time. So that means you can say that your distance here is represented by s, which is equals to v, the speed, times time. Okay. Yeah. So what's the variable speed now? So see here. So variable speed means like for equal interval of time, you're moving a different distance. So now here we have this on the right hand side, we have a graph where it is on the x-axis it's a time, on the y-axis it's a speed, right? Or sorry, distance, right? So now what does the slope of this line gives you? The slope of the first section here, right? So now if you see this interval of time, delta t1, delta t2, right? This interval of time are equal. But in this equal interval of time, you are moving a different distance, delta S1 and delta S2. So distance covered is different. So now since distance covered is different, so that's why you are getting a different slope of a line. You understand the slope, right? You guys understand the slope means, right? Okay. So I think like I'll stop right here for today, and then we'll continue on Tuesday about this one-dimensional motions. And now it's like a 7:45. I will give you a break of 10 minutes, and then we'll come back in the same Zoom meeting, and then we'll be doing a lab. Okay, make sense? So it's 8:46, so that means 10 minutes is 57. Okay, so let's do 7:57. Okay. Hello all. Are you guys back? Good. Everyone is so back. So this 10 minutes is like really fast to eat my dinner. So you guys had your dinner? Okay. Okay, good, good. So now, if you guys go to your Blackboard, in your Blackboard, and there is like a section called like online lab on the left, and you might see what's called like lab one measurements and uncertainties. Do you guys see that? Where did the chat go? Where did the chat go? Where did the chat go? Oh, yeah. Okay. And if you click that one, and then on the top one, so lab one, so measurement lab questions. So there are like a questions. So in this lab, but there are like three problems in these questions that you need to read the lab manual first to do those three problems. But others are about the significant figures, rounding up the numbers, and all those things. Okay. And if you click the lab manual, yeah, it will open up a PDF file. Can you open the PDF file? No. What does it say? Okay, that's what. Let me see. Oh yeah, so you have to use your like a ACC.
Yeah, I don't have a Microsoft, and that's what it wants.
It is Microsoft.
Yeah,
You can use
it won't let me.
you.
Actually, I'm gonna try my ACC, but I don't have a Microsoft account, so I don't think it'll work.
This one.
Oh, it's telling me to update my password. So I guess logging in with my ACC ID it worked, but it wants me to make a new password.
Okay. Mhm.
Oh, it still says it didn't work.
Yeah, I'm able to log in with my ACC ID. It doesn't let me. Okay. You know what? I will just make this thing.
Yeah, it says actually that didn't work. It made me feel like it was working, but it didn't.
Okay. So I'll just give an access so that everyone with a link can open. Just a second. I don't know, last time it worked, but this time it didn't. I don't know why. Share. And then view settings. Anyone under the person. Yep. Copy link. And then everyone use this link. And then can you open with this one then? Okay, good. Okay. And then this one, another link. And then you will also need, let's see what is in my Word document. Edit this one really quick. Oh my. Let me do one more thing here. Okay. Hold on a second, I'm trying to have another one. Where is M? Okay, here. And okay, and for the Excel file, so there's a link. This for another Excel file. Okay. So you guys can access the file, right? Okay, so now you're the link for the Excel file. I sent you another link here. Okay. Okay. So now let me share my screen. Okay. So this is the measurement lab. So in this measurement lab, we are going to use the vernier caliper to do our measurements. And then we will also gonna do the use of significant figure, decimal places, and also like, how to calculate the error. Okay. So generally the vernier calipers, so this basically they look like this, as you can see. What is the camera? This mic here. Okay, let me get rid of this background. Um, video settings, and then where did things go? Blur adjustment. This video setting. Okay, here it is, my video settings. And then background, what is the background? Background, and then I would say, can I say no one? None. Yes. Okay. You can see so now, generally this is how the vernier caliper looks like, right? And then you can pull this, and there's a clock, right? And if you want to measure anything, like say, you guys can see my camera, right? So there's so much yellow. So
Yes.
and then if you want to measure the length and width, right? So suppose this thing. So if you want to measure, so you're going to put this thing in between the vernier calipers, right? And then you measure its width. And then if you want to measure this height, you put in this one and you in between, and then you will read this reading, okay? And now if you have like something circular object, then you see there's another kind of like a teeth here, right? So this is to measure the distance, internal distance, internal diameter of like a circle. Like here, you pull this one, and then here, you measure this diameter in this way. Make sense? So if you want to measure the inner distance, you'll use this part of the vernier caliper. You want the outer, you'll use this part of the vernier caliper. And in this vernier caliper, you have these different readings. So here, on the main strip, this is the main scale reading, okay? And down here, this is a vernier scale reading. And let me open, and if you guys open that, if you go to this lab, measurement and uncertainties, and then join the class, use the class code to join, right? So then I can go here to measurements. Here. It's the same thing here. So vernier caliper. I'm going to show you this one, right? As you can see, and with this one, you can zoom in and zoom out, okay? So if you click and then it can zoom in, okay? And zoom out. So it can be done. And also if you click and drag, you can move, right? And then if you want to move this object, you can move this one, you can move this one. And with this orange dot, you can drag and open this vernier caliper. Make sense? You guys can see, right? You guys can see my screen, right? Yeah. So now, if I zoom into this one, this one here is a main scale, okay? And this one here is a vernier scale. So in shortcut, it is written as a VS, and this one, it is measured, named as a MS, main scale, or MSD, main scale division, and this is a VSD, vernier scale division. So now as you see these lines, right, so that there are 10 lines, right? But in the main scale, these 10 lines are not exactly overlapping. All of these lines are not overlapping. Do you see this one? As you progress further, go right. So they are not exactly aligned with these main scale divisions. You see that, right? Right? Yeah. And now the 0th one is coinciding with the 0 of the main scale, and the 10th division of this vernier scale coincide with the 9th division of the main scale. Right? And here, since this is in a centimeter scale, so like here, this main scale is in a centimeter. So this is a centimeter. So one division of this main scale is 0.1 centimeter, or we can say 1 millimeter, right? And as you see here, this vernier scale differs with the main scale by this small amount, right? So there's this difference that you can see. That means you can drag this one and you can make sure this line is aligned. But now when this line is aligned, only this line will be aligned with the main scale. None of the other lines are aligned with the main scale. Do you see that? So that means our vernier scale will be that sensitive. 1/10 of a millimeter it can measure with this device. With this device, we can measure, so, right? And now again, if you move this one, now when you align the second line, second vernier scales aligns, none of the other aligns. Similarly, you can move third, when third aligns, none of the other aligns. Now when you move, fourth one aligns, then fifth one aligns, right? And the fifth one aligns, none of the other things aligns. Now look at this 0. The 0 has moved all the way to the half between this 1 millimeter. You see that? So that means when the fifth division of the main vernier scale aligns with any of the main scale, that means it has traveled how much distance? Not 0.5 centimeter, 0.5 millimeter, not a 5 millimeter, 0.5 millimeter, right? Because this is 1 millimeter, right? So far. Now, if I move this sixth one, if I consider the sixth one, how much did we move now? It is like a little bit more than a 0.5, right? So how much? 0 point, how much? What do you think? If I say the sixth one, 0.6. And same thing now, if I do 7, then we moved a distance of 0.7. And similarly, if I move another line, then eighth one moves. Oh my goodness, this mouse. Okay, eighth one, if you move this eighth one, so it moves all the way to the eighth. And if I move 9 one coincides, so it moves 9. And now if I make this 10th one coincide, it aligns. So that means now in our vernier caliper, with this scale, we can measure 1/10 of a millimeter because of this, right? So now, so different vernier caliper will have a different least count, right? As you see here, so this distance is 1 millimeter. So now we can measure a distance which is much, much smaller than like a 1 millimeter. This is a vernier caliper. So now we will use this vernier caliper to measure the diameter of this circle. Put it here, right? And then you go and read here. So now when you read here, so what is your main scale? So the main scale that you will read is where is the 0 of this vernier scale coincides. So 0 of here is here, but this 0 does not coincide with any of this main scale. So now your final reading will be a main scale reading, which is just before or right at the 0 of this vernier scale. But now, since this 0 of this vernier scale does not coincide with anything, so the measurement will be, the main scale reading will be this, which is 1.8, right? 1.8 millimeter. Now, so what will be the next one? Now we'll look and see here which one coincides. So now here, this vernier division number 2 almost coincides here, right? So now you can say this is my vernier scale number 2, right? And then you have to multiply by the least count. Now, what is the least count? Again, if you go to this here, so least count is like a minimum measurement, the smallest distance that it can measure using a vernier caliper. Right here, so it is sensitive. This is distance that you can see how much it is off, right? So the value of one main scale division in this our measurements, yeah, in this one, what is our main scale reading? This is like 1 millimeter, right? So value of one main scale division divided by the number of head scale divisions. So that means how many this vernier scale division, right? So that means 1 divided by 10, right? So 1 millimeter divided by 10. So that means you can measure 0.1 millimeter in this particular vernier caliper. Make sense? Because there is like a this distance is 1 minuscule division is 1 millimeter, and how many of those there are? There are 10. So that's why it can measure, a least count is 1 divided by 10, 1 millimeter divided by 10. So it has 0.1 millimeter. Make sense?
That makes sense, but could you explain how the when you actually measure an object and they're not aligned, which line you're trying to line up?
Oh, okay. So now here. So now let's see. Right. So now if I will take this circle, right? I'll just bring it here. So I see this is lined up here. Okay. So now other side of this vernier caliper, I want to line up here. I move it and then there. Then I say like, okay, this is the diameter of this circle, right? Now I want to go and read this scale, right? Now when I look at this scale, this vernier scale does not coincide exactly with the main scale, right? So now in this case, your main scale division will be what? A division that is before the before this vernier scale. This is my vernier scale. What is the main scale division? My main scale division will be this one, this line. Okay, makes sense? Now, this 0 of this vernier scale is moved by how much, right? That you can see by looking at this, which of this vernier division coincides with the main scale division. So now like 1, does it coincide with the main scale, this one? No. Does this coincide with the main scale? No. Does this coincide with the main scale? No. Does this coincide? No. But this one coincides with the main scale. So now the vernier scale reading will be 5. Make sense? Yes. No, only 5. 5 on vernier scale division. Just a 5. Right now. Yeah, 0.05 that you mentioned, because you are already multiplying with your least count. Make sense? So that's a vernier scale division is 5. Then you multiply that with the least count. What was our least count? 0.01. Multiply that 5 with 0.01 least count, and that will give you 0.05, whatever you have this value. Because vernier scale division has no units. When you multiply with the least count, then only it gets units, right? So now this 5 multiplied by the least count. Now if I go here in the manual, right? So this is my least count, 1 main scale division minus vernier scale division. That's the least count. Or we can also determine by this value here. So this will be easier to do the calculation for the least count, right? And now TR means the total reading. So what is my total reading? So as you said, Dustin, so 1.8 centimeter, not millimeter, 1.8 millimeter is your main scale reading. And CVD means coinciding vernier division. C means coinciding. Which one is the coinciding vernier division? So in this case, it will be 5 times LC. What is your least count? Your least count is 0.1 millimeter or 0.01 centimeter. Make sense? And that will be your total reading. Okay? Make sense? Yes? Does that make sense?
So when you were talking about the accuracy, how you annotate that, would you write it as 1.8 millimeters plus 5 times 0.1 and leave the units out of it? Because you said,
Yeah,
I think, leave all the units.
so this is like a main scale reading is like a 1.8 centimeter, right?
Mhm.
And then your coinciding vernier division is 5, right? Times least count is 0.01 centimeter,
Oh,
right?
sorry. But do
Right?
you put the
And you add them up. Then you add them up, everything.
Okay.
And then what will be 1.85 centimeter. Make sense? Make sense? So there will be 1.85 centimeter.
I think I just need some practice.
Okay. Yeah. So there's a table, like in an Excel, there's a table. So as you do it, so you can do it. So that will be 1.8. Now your uncertainty will be the value of the least count, because this vernier scale and every measurement has uncertainty, right? So only because in this one I can zoom in and then see if it really coincides or not. But in the real instrument, you might not be able to zoom in, right? So there will be like chances that you might go off by like 1 division. Make sense? Right? In a real, your vernier scale will be off. Not even this one, maybe this or something like that. So which will be like hard to see, like as you see in here, this scale. This is how it looks like, right? So in that conditions, so there's a chances of like some uncertainties as well, right? So now your uncertainty in this case will be your least count. Okay. So now as you see here, where is my Excel file? Can I open my Excel file? Yeah. So yeah. So that's your least count here. So this is a vernier, which vernier caliper you are using is 1, 2, or 3. So now this is like a general questions to everyone. So this is I just mentioned this is like a least count is 0.01 centimeter, right? So now I have another vernier caliper, version number 2. Now in this one, what is my least count? Can anyone tell me? Again, the main scale is like in centimeter, and it has like 20 division. 0.02, how did you get that?
I don't know. I just doubled it because we had 10 the first time and now there's 20 there.
1 divided by 20. Yes, that's 10.
Right. We have that. And the first time we did 1 divided by 10.
Now you have to do 1 divided by 20, right?
Right.
One. So again, this is like what? 1 millimeter. That is like 1 is like 1 millimeter, not 1 centimeter. So again, write down the units, right? So it's a 1 millimeter there. So that means 0.05 0.005 centimeter, if you want to do it like, right? So now if you see this one, if I zoom in this one, if I go ahead and then zoom this one, and then I bring this one down, see, so this gap is like really small compared to the earlier version of vernier caliper, right? This gap is like half of what we had. Earlier, what we had like a least count 0.01. So this is like even that 0.0, sorry, 0.1 millimeter. Now this is like 0.05 millimeter, right? So because this is 1 division divided by, so meaning what does this 20 means? So the space between these two from 0 to 1 is divided into 20 space. So meaning, let's see, What does that mean? So now this is not concerning, only 0 is concerning, right? By the time 0 goes to like 1, how many times we have to move this one? I moved it one time, right? It coincided with 1, right? Make sense? Make sense? Now, one time I moved it. Now, second time I moved it, this second one coincides, 2. Now, so now as you see, 0 is moving. 0 already moved like from here to here 2 times. Now I move this one again one more time. Third time I moved it. So 0 moved from here to here. This third time is coinciding. Now if I keep on doing, fourth time, fifth time, sixth time, seventh time, eighth time, ninth, 10 times. After I'm moving it 10 times, it reached the half of the distance between 0 to 1 millimeter. So that means to move from 0 to 1, how many times do I have to move? Divisions. So 20 times, right? Now 11 times, right? 12 times, 13 times, 14 times, 15, 16, 17, 18, 19, and 20. After I move 20, so that means the space between this 0 to 1 millimeter is divided into 20 small parts. And that one small part that we moved is a least count. Make sense? Make sense? So that means 1 millimeter divided by 20. That 1 millimeter divided by 20, right? So this is 0.05 millimeter, right? So, and then, so you go ahead and then do this, right? And then, so you have to measure this blue diameter, and then you select your vernier caliper that you are using, right? 1, 2, or 3, right? So use that one, and then it will give you, and if you're not selecting anyone, it will just say, please select the vernier caliper, right? These are wrong, some numbers that I have. I don't know why we have this. Okay, so you can go ahead and download this Excel file and then work on it. And then interesting, like so you can only select this one, and also make sure when you are writing your numbers, you are writing in a correct significant figures, right? So this one here, 0.100, right? Is this right? No, this is not the right way of writing these numbers. So now, is that formatting? Decimal places, okay, here. Then decrease this number of decimal places. Here, select 1, decrease this number of, what happened? Yeah, so you can use this increasing and decreasing in Excel and use the correct number of decimal places and a significant figure, okay? That's what I will be looking for this in this lab as well. How significant figure you're using it and how you're doing it, right? So in this case, the uncertainty for this one, so diameter, right? What will be the uncertainty? Uncertainty will be this one value, least count, right? Now, when you are calculating the radius, what will be the uncertainty? Since you divided by diameter, like, you took this, right, big length, and you divide by to calculate radius, your uncertainty will be also smaller. And then when you calculate this length and width uncertainty, right, for that rectangle, and now here you will calculate this area, right? In this, when you calculate this area, now you have to use this formula to calculate this uncertainty and then see what is the uncertainty. Okay, make sense? And everything here is written in millimeters here. Least count in millimeter, this main scale region is millimeter. Everything I have given you guys, the units, everything that you report in a millimeter here. Okay, make sense? So they are like, and then there's a purple inner edge. So like, let me go here. And in this one, yeah, this one, right? This purple object. So now you calculate the inner edge. What you're gonna do? You're gonna use this, the upper one, and then you try to manage here, put it here, and then you read these numbers. And are you satisfied? If you are satisfied with your now placement of this thing is exactly here or here, and then if you're satisfied, and then you go and read these measurements and then see what is the inner space between this thing. Okay, so even though it's simulations, like this is like exactly what you do in a real life vernier caliper experiment. Make sense? So go ahead and use that class code and do the lab, and I can see you guys as you are doing it. And if you have like any problem, I can see it. Okay? Any questions?
Where
Oh,
is that Excel
the
sheet?
class code? The class code is there, right? So lab code. So it is already posted in the Blackboard again, but I'm gonna paste it here again. It's like, see here in the lab one measurements, and then there's a lab code CNFT WWAV, right? It's written there. Do you see that? Yes, download the copy of the spreadsheet in your computer and then fill out the numbers as you are making your measurements, and then save it and then submit it in the lab one. Okay, so like, okay, let me show you this one, how to submit this lab report as well. Hold on a second, right? So this is a lab one, so you can see my screen, right? So if you click this one, so there's like, this one will open up your GeoGebra, this one will open up your lab manual, and this is in a GeoGebra, this is the code that you're gonna use. And if you click this lab, then you have all these three and submission, upload a file and then submit. Make sense? And it also displays you your due date by when you should be submitting this one, right? So even though the due date is like a next week, I would highly encourage do it today during the class, so that if you have any questions, you can ask me and things. Make sense? Okay, start the share. Excel file is okay. You should submit it before October 2nd midnight. Make sense? But I would encourage you to work right now. Okay, understand and everything, how to take data. So Excel sheet is in the 11, okay. Excel sheet, copy link. So Excel sheet is here, Dustin. I'm sorry, like, the link that I put there, it didn't work. So next time when I put the link, make sure that it does not require you to put the username, login or whatever, so that you can have an access. Maybe I'll put it in a Google Drive, so it will be much more easier for you guys to access maybe. Okay? Any questions?
I have a question actually. So do we pick which version we
Yeah.
use?
Yeah, just pick anyone.
Okay. And is it supposed to be the same version for all of them? The diameter, the radius, the rectangle?
Yes. Only the like your list count will be different. So now the way I asked, I would showed you how to calculate the list count. You can see and then do it.
Okay. Thank you.
And we only need to do one, not all three, is that correct?
Not all three. Yeah, just one.
Just one what?
One version of vernier caliper. You don't need to do all vernier
Oh,
caliper.
but all the little things like the diameter, the radius, the rectangle.
Mm-hmm. So I mean to say, like, just use one version of vernier caliper. You don't have to do all three versions of vernier caliper. You know what I mean?
Yes.
I might have to restart my computer. Looks like.
Okay, I have a question. I guess because now that I'm doing it by myself,
Uh-huh.
I blanked a little bit. So for the main scale reading, it's the top
Yes.
of the ruler or whatever. I mean, of the
And you're
veneer.
using
Yes.
and
And
you're
so,
using a red circle right now, right? The red
yes,
circle.
I'm doing the red circle.
Mm-hmm.
And so I'm trying to read on the thing, and I guess I'm confused about like which line is supposed to be my reading.
Okay, so your 0 is not coinciding with any of the main scale, right?
Correct.
So now 1.8 is like before 0, right?
Yes.
So now your main scale reading is 1.8 centimeter.
Okay, I see the 1.8 on the ruler, but I guess I'm just confused as to why that's my reading for the ball.
Now looking, you need to find which of the vernier division is coinciding with the main scale division, right?
Right.
And now when you look at it, which one looks like more coinciding? Which one?
Oh, the one that we think is the closest to it on
Yes.
the third line?
Third line?
No,
No,
not the third line.
no. Okay.
The fourth line?
Did you check?
1, 2, 3, 4.
So in the vernier divisions after 0, there's the first one. Is it coinciding with the main one?
No,
Second one, second division. Is it coinciding with any of the main scale division?
no,
Third one, is it coinciding?
no,
Fourth one, is it?
no,
Fifth one, is
no,
it? Sixth one,
no.
sixth one. Zoom in and see.
I am zoomed in. Let me do some more. Come in. Oops, I moved it. Dang it.
Or you moved your
Yeah,
caliper.
by accident.
Mm.
And I'm not tech savvy, so I'm learning how to
And
like
that's fine. That's
zoom in
fine.
on my MacBook.
Yeah, that's fine.
Okay, so
Now your circle, red circle, your vernier. Okay. So now
Yeah.
which one you think like is coinciding?
Well, none of them are.
The first division, I can see the first division of the vernier scale is coinciding with the main scale.
Then I must have mine in the wrong place then, because it's not.
Okay. Let me
Let me move it some
get a
more.
breakout room. Uh, okay, I'm gonna take you to breakout room. Is that okay?
I'm sorry?
I'm gonna take you to the breakout room so that I can.
Oh, okay.
I'm going to join the breakout room. So how are you all guys doing?
I had a question about
Yes.
could I ask like specifically to like which Vernier
Uh-huh.
scale?
Okay.
So like on scale 3, like the
Mm-hmm.
value of like one main scale division would be on the top, right? It's like one.
Yes.
So like
Millimeter.
so from the 0 to the 1, that's a millimeter, or it's a centimeter, and then it's one
Zero
millimeter, like
to-
the smaller.
yeah. Yes. 0 to, okay, so let me share this one. Is 0 to 1 is a centimeter.
Okay.
This centimeter is divided into like 10 parts, which is like 1 millimeter, right? And
Okay.
then from this 1 millimeter is divided into 10 parts here. Make sense?
Makes sense. So then like that would just be 1 millimeter divided by like the main scale division on 3 is 10.
Yeah, so main scale is like 1 millimeter, right?
Uh-huh.
And how many vernier division do you have here?
10,
So 1 divided by 10, 1 millimeter divided by 10.
which would be what would that be?
0.1 millimeter.
Oh yeah, 0 point or yeah. I was looking for the prefix, but there wouldn't be one for that.
Okay. Right. And so this is what it is. And Excel file, download that Excel file to your computer. Okay. And as I was talking to here, so right, so these numbers, don't put these numbers, but I don't know why you guys are, okay. So you should download this file, okay? Everyone should download this Excel file first and then work in Excel in your personal computer. Make sense? Don't do it here. Any questions?
The uncertainty, is that a main scale? So like if we're at centimeter scale and we're using millimeters, would our uncertainty be plus or minus 1 millimeter?
No, that will be your list count.
Oh, plus or minus 1 list count.
Yeah. So what is it? What is your list count? Which vernier caliper you are using? Based on that one, that is your list count, right? So here, that is your list count, right? That will be the uncertainty. So if you are using like version number 1, that is like 0.1. Version number 2, so it's like a 1 divided by 20, right? That's your uncertainty. Make sense?
Okay, thank you.
So why that uncertainty? Because when you see when there's coinciding, yes, you might, if you zoom in and it's like, okay, some say like this, some say this is like coinciding, some say this is coinciding, some say this is coinciding, right? We really don't know, right? So based on that one, to give a room. Make sense?
Yep.
Okay. So you will upload into the Blackboard. If you click that lab itself, where did you see that? Okay, so okay, let me share my screen. So if you go to the lab, right? So you see these two. So there's a lab 1 measurement, 11 questions, right? So let me see what it's at so that I can. Sean, you see this one, right? My screen, do you see my screen? Sean, you there? Yeah. So now in this one, if you click this one, it'll open up. And then here you can upload a file. Click upload and then submit. Okay. And this question answer is due by midnight. This particular one, there are like a question answers midnight. today by midnight. Do this question answer. It's all about the significant figures and list count of the Varney calipers. So now you know the list count. It doesn't upload. Let me say, let me do one thing. Excuse me.
And the coinciding Vernier
Uh-huh.
divisor, that's
Uh-huh.
just a number. Is that
Sorry?
correct?
Sorry?
The coinciding Vernier division, the CVD, that's just a whole number.
That's like a what number of like a Varney division coincide with the main scale?
Or so
1, 2,
like
3.
the diameter where it says like the main scale reading, and then the CVD, like it
Yeah,
the
CVD
coinciding.
is like a whole number, like a
Okay, yeah. So it's just like a line
coinciding one.
fifth one, so then there would be like a 5.
Yes, if it's a 5, then it's a 5.
Okay, awesome. Thank you.
And in the next column, there's a TR, which is total reading, with the main scale reading plus CVD times list count. Okay.
So in my case, like it went above the 4.8 or like 4.8 or like the yeah.
Uh-huh.
So then that would be like the millimeters 4.8. And then the coinciding Vernier was on the 5, so then it would be 4.85.
Yeah, your is like you might be 48 millimeter, not 4.8 millimeter.
Say that one more time.
You said 4.8 centimeter
Oh,
or millimeter?
no, 4.8 millimeters. So yeah, 48.
Millimeter, yeah. 48 millimeter. Yeah, don't get confused with the units.
So then like the coinciding one was the 5th one, so then that would be 4.85 centimeters.
Yes. And everything here is like in a millimeter. So all this table here is in millimeter. So make sure you write down everything in a millimeter, okay? Okay.
Will do, thank you.
So Mariam, so you should be able to upload the file. I don't know why you're not able to upload the file. You should be able to upload the file. Okay. So Alia, okay. So you need help, Alia? So okay, I will take you to the breakout room then. Alia. Anyone else having any issues or problem? How to use it?
I think I got it all. What I was curious about is the uncertainty when you get to figuring area, since you have uncertainty in two different dimensions.
Uh-huh.
Would you have to square your uncertainty or like add them together?
So, okay, so let me post this note to you guys because let me see what do I do this one. Okay. Okay. So the one that we did today, right? So I'll upload these notes and so that you can use the formula to calculate the uncertainty. Okay,
Perfect. Thank you.
does it make sense?
Yep.
Okay, so let me go here and yeah.
I had a quick question. You explained like when your veneer caliber was on 0,
Yes.
like when the line is like perfectly on 0. You said that's what I use as my what's it called?
Hold on a second. Hold on a second. Hold on a second. I'm trying to upload the notes
Okay.
and then here so that you guys can do the calculation for the area. So yeah, what was the question? Again, one more time.
Yes, so I'm currently doing like the blue circle for my
Okay.
veneer caliber.
Uh-huh.
And I
Okay.
remember you saying something about when it was on 0, but I couldn't remember if you said to use that or the next one that it was closest to.
If your zero vernier division of your vernier scale coincides exactly with the main scale, then your vernier division is 0.
Okay. I
If
was
it,
just making sure.
yeah. So let me see your screen. So in your case here, yes, your 0 is exactly aligning with like a 4.8, right?
Yes.
So now in your case, this vernier division will be 0.
Right.
CVD will be 0. Okay.
Mm-hmm.
Okay.
Just making sure. And then, so for the uncertainty,
Mhm.
what, I guess, so the next one, like how much it's off by, or?
Uncertainty is like how much you're unsure, right? So whenever
Right.
you move your vernier caliper, you might be off by like a 0.1 because right now it's a simulation, right? But when
Mhm.
you really do it, and also in the simulations, right? So when you put your circle, the edge of this vernier caliper might not be exactly on that one, right? You might be off a little bit, right?
Yes.
And that uncertainty is the least count that you have
Oh, okay. So is the uncertainty always the least count?
for your diameter, yes.
And then for the radius, it's just half that?
Yes.
Okay,
And for area, you have to calculate.
right.
So I have given down the formula in the notes, right?
Yes.
I have to use that formula to calculate the uncertainty in area. Okay,
Okay. Yes, thank you.
you're welcome. And that is I have given only for the like a circle and for like a rectangle, then you have to do the length and width, right? Uh,
Right.
so you have to use the same length and width uncertainty.
I know I'm just moving slow, doing the circles first.
That's fine. That's fine. So Delise is not here. I don't see Delise working on it. So this experiment is at least giving you an idea how to use a vernier caliper, right? And how to do the measurements.
Yeah, I almost want to go buy one, like just so that I can see.
Yeah, it's not expensive. It's like maybe like a $5, $4, something like that. You can find in a Northern Tools or something like that.
Literally,
Yeah.
I looked on Amazon already.
Oh, okay.
Professor, once we have that submitted to you, do we just start working on the lab questions?
Yeah.
So for the radius,
Uh-huh.
would we just like divide the MSR by 2, like whatever we found for the diameter, or?
Your total, yeah, whatever your diameter you get, the total reading, you divide by 2,
Oh,
right?
okay.
Because
Yeah.
the radius is the half of the diameter, right?
Mm-hmm.
Yeah.
Okay, thank you.
You're welcome. So Gabby, are you using the same Excel file from the links? Download in your computer. You are working on the thing. So
I am using the one on my laptop now.
oh, you downloaded, okay, because I see like you still like changing the numbers, so that's why I was like wondering. Okay.
Still, I'm using the one on my.
Okay. Okay, that's good then. That's fine.
Do you see my rectangle numbers?
Rectangle number, no.
Oh, okay, so yeah, I'm using the one on my laptop now.
Okay, so good. Cool, cool.
I have a question. I think
Yeah.
so you were saying before that like the head, so like I'm looking at like the difference between the caliper version 1 and version 3.
Uh-huh.
I'm not sure if I messed up my understanding. So like on caliper version 3, it would
Uh-huh.
be 1 millimeter divided by the head count of 10, right?
Yes.
But wouldn't it be the same thing on for caliper version 1?
Yes.
But they seem smaller. How does that
Yes.
work?
It's just like, so again, so that only thing is like there, the separation is like it's bigger, right? But again, it is moving the same thing. Does it make sense? Just to make it like reading easy.
Count
So
on the caliper version 1 and version 3 are the same?
yes, the list count is same.
Huh. Is it just because it's scaled differently? Like
Yes.
it's
It
scaled the
just it just like, so that part, whatever. So instead of using like a 1 millimeter, so it is using a 2 millimeter and keeping the same distance separation.
Oh, okay,
You
okay.
see that? So
Yep.
just to reach like a 2 millimeter, it is using like it is already reaching 1.9 millimeter, and then remaining is a zero point 0.1 millimeter. Make sense? So now the vernier scale can be measured. So that's why I made like 3 different versions. So that's why in this vernier scale, so if the vernier divisions are like separated wide, so that it will be easy on eye to see, right? Right? So compared to other one, the vernier divisions were like really close to each other, right? Make sense?
Okay.
Right? Just to make it easy to read, vernier scale can be designed in different ways. So just to give you guys that an idea if you figure it out or not. So that's why I was like doing that one. Make sense?
It does. How would I measure the uncertainty? I forgot about that one.
Uncertainty of what?
Of the diameter.
Uh, just a second. You, I was just trying to send an Excel file to, yeah. So if you want to find the uncertainty of diameter, that's the least count.
The least count is the uncertainty?
Yes. That's the minimum scale that you can measure, right?
Okay.
Right. So that's the minimum. So you can go off by that minimum. You cannot go off by less than that one. So it can be like a least count or like a twice of the one, but for this purpose, you said that that's the least count because that's the significant figure that you can get, right?
Right, right.
Yeah, and that's what that if there is some error, it will be error in that particular decimal place. Make sense?
That does make sense. Thank you.
Yeah.
I have another quick question. I'm trying to do like the width and length of my rectangle. How do I
Yes.
like, turn the rectangle to do like,
Rotate.
yeah, like I don't know how to rotate my rectangle.
Okay. So in that rectangle, you see there's a little bit of lip on the bottom
Yeah,
right corner. So click that one and rotate,
I am clicking. It's not working.
and then click and drag. It will rotate.
Oh, okay. Thank you very much. I was like, I don't know. Okay. But okay, thank you.
You're welcome.
I'm not tech savvy at all. Like literally, I've had this MacBook for so long and I don't know how to scroll still. So,
Uh-huh. So you rotated. You did it.
did you watch how long it took me to do that though? Like, even after you told me how to do it, I was like, okay, so now I click it again. I still didn't have it. Sad. It's sad, but yes, I did it. Thank you.
You're welcome.
So what do we do to find the uncertainty for the area?
So we did the in the class we did calculate the uncertainty for the area, right? So x times y and pi r squared, right?
You talking about yesterday?
No, the today, right? And I have uploaded the file. What?
Oh, okay.
Yesterday? You're not paying attention in today's lecture? That's the very first thing that we did today in the lecture.
Let me go check.
Ah, so you had your computer on and you were like running away from the lecture class. I see you.
No.
I got you. So that's the bad thing about the online class. I don't know who is in the class and who is not. I just see the black screen with the first letter of your name, D-A-L, right? So I trust you guys to be in the class without turning on your camera, but don't take advantage of that one. I just need to help someone in a breakout room, so I'll be back after I help, okay? Okay, guys, everyone, it's time. So if you need to work more on this one, you can keep on working on it. Okay. And by the way, by today midnight, so the lab question answer is due. Okay. The question answer, this lab report, the whatever the Excel file that you're working on, it is due next Wednesday. But the lab question answer about the significant figure and all those things, it is due tonight. So please try to do that one and submit tonight by tonight. Okay.
I had one quick question, is that okay?
Sure.
For the spreadsheet on like for the radius, if like for example, if it's an odd number and you divide it by 2 and it becomes that 0.5, how would that work?
Sorry. Oh. So radius meaning what? So like,
So for the measurement, like I'm using like the diameter and I'm dividing it by 2 to get the
yes.
radius. So
Mhm.
it's an odd number, like it's 27.
Uh-huh.
Would it be 13.5 for the millimeters, or would it be just like,
Yeah, 13.5, yeah.
but that like works for the significant figures?
So let me say here. So what is your diameter you said?
The diameter is, let's say, 39.
39, right? And then if you divide by that, so that and it will be like, and what will be your uncertainty?
Say that again?
What will be your uncertainty?
It would be 19.5.
No, no. I mean, it's like if you for the radius, right? You have a diameter, right? And then you said diameter divided by 2, that will give you radius, right?
Right.
And what will be the uncertainty for the radius?
The what of the radius?
Uncertainty.
Oh, the uncertainty would be uh 0.1? No.
No. So
It would,
0.1 is your least count, right?
yeah,
What is the uncertainty? 0.1 divided by 2.
2.
And what that is?
0.05.
Point, 0.05, right? How many decimal places you got there?
Uh-huh.
How many decimal places do you got there?
2.
And now how many decimal places you have in your radius?
3.
So round, have like a decimal places to 3 then. 2, sorry. Because your uncertainty, whatever the decimal places you have,
Okay, so you would just round it up?
yes. Because your measurement cannot be more accurate than your uncertainty, right? For an example, like what did you say your radius was?
39.
39. So 39 divided by 2, that will give you 19.5, right?
Right.
And your uncertainty will be 0.05.
Right.
So 19.5 is still well under this 0.05. So it should be 19.50.
Oh, okay. Okay.
Make sense?
Uh-huh. So in the same way, like let's say the blue or like for a different one, if the diameter is 18
Mhm.
and the uncertainty was 0.05.
So now again, remember, so when you said diameter is 18, is your measurement only give you like a no decimal places? What does your measurement we're gonna give you?
Oh, no way I can
18 point what?
18.3.
18.3, right? Or
Uh-huh.
like if it's exactly 18, then it should be 18.0 because
Right.
you can measure up to 1 decimal places. You cannot neglect that 0 because that 0 decimal 0 is a significant number.
Right. So the 18, it would be 18.3 divided by 2. And then I know my measurement is as good as up to that 0.05. So 18.3 divided by 2 is 9.15. So
Yes,
be like acceptable.
yes.
as it is.
Uh-huh.
Okay. Could I run one more by you just for practice?
Yeah.
So like let's say the diameter is 39.2. It would be 39.2 divided by 2, and it's 19.6, but that means it would be 19.60.
Yes.
Okay, all right. And then how would that work for the area?
So in an area, so if you have paid attention to my class, the very first thing that we did, right, the scientific notations and calculate the uncertainties, right? We did that in a class. And if you look at the notes, if you open up the notes and go to the second page in the notes, almost all the way to the bottom. So area is pi r squared, and then I showed you how you calculate the uncertainty. So area is A plus minus delta A. What is delta A in that condition?
Uh,
So it's uploaded in the Blackboard. Can you upload open the notes?
it was at the very bottom, right?
Yeah, so the second page.
So say that again. It was the
Can you share your screen?
yeah.
Scroll. This is like a last week, like this is Tuesday. Today's notes. Open the
Oh,
today's. Oh, don't click that. Oh, okay, yeah. Oh, you go through the notification. I don't go through the notifications. So, okay, scroll down. Scroll down. End of the second page. I said end of the second. End of the first page. Second page. There is, for an example, area of a circle with radius 2 centimeter. A equals pi r square, right? And how do you
right.
calculate the uncertainties? And then R, I said in the A equals to pi r squared, so pi r times r, right? R is what? R plus minus delta r times r plus minus delta r. And I've shown you all the steps to derive it. And then we got pi r squared plus minus 2 pi r delta r.
Okay.
That is my uncertainty in the area.
So it's that plus or minus 2 pi r delta r.
That is your uncertainty for the area.
Okay, but I guess as it relates to this one, the delta r would be what?
Delta r will be the uncertainty in your radius.
Or
And
that r would be the radius, correct? Or would it
R
be
will be the radius, R will be the radius, delta R will be the uncertainty in the radius.
oh, okay.
And
So
we have that both.
and then the uncertainty would be still the 0.1
Why? How do you know which one 0.1? Uncertainty of what?
for the area of the circle. No, it would be
You have to calculate that one. I don't know. I don't know what your radius is. I don't know what your uncertainty in the radius is. So you have to calculate 2 pi r times delta r, and that is your uncertainty.
okay. But but that's how you calculate. How do I say it? So I start off with like the radius. Let's say the radius is 9.15 was the one that I did before.
Okay.
You would get like 9.15 pi or time squared times pi to get to get the area of the circle.
Yes.
And then you would be plus or minus the uncertainty would be 2 pi times
Uh-huh.
9.15
Uh-huh.
times 0.1.
What is your uncertainty for radius?
How do I calculate the uncertainty of the radius?
You just said earlier, right?
But that was to get the
In your Excel file, what did you put your uncertainty for the radius?
that's what I was asking. Like, how do you get to the uncertainty of the radius?
So you see,
So for the rate, you just use for the radius, the uncertainty of the radius. Okay, okay.
yeah.
I myself up. Sorry, I was running in circles. All right, thank you. I appreciate it.
You're welcome. Okay, so does anyone have like any questions before we leave? So, okay. So I believe this, yeah, you have an access to the lab manual, right? Don't you?
Access the sheet, I just can't access the actual like manual.
Lab manual?
Yes.
Oh, okay. So just a second. Settings, anyone with this? Can you deploy, copy link? Yeah. So use this link. Can you?
Yes, thank you.
So yeah. And if you want, you can download that manual. Okay. Any other questions?
I have a really quick question.
Yes, go ahead, Ali.
So for the rectangle, I think I'm just confusing myself. Like the red rectangle, the part where it says like uncertainty, that isn't like in today's lecture we calculated like how to find it for like area, like length times width. That's not that, right? Like it's just
Area is length times width, right? X,
okay
Y,
for the
right? Area for rectangle is length times width, right? Which is X times Y.
yeah, but on like the Excel sheet, it just says like red rectangle and then length and then it says like uncertainty. Is that formula or no?
So now when you measure the length of a rectangle, what is the uncertainty of the measurement of length? What is
That's from
it?
today's lecture, right? That's like delta X. I think.
Yeah, so length is what? Delta X, right? So what is your uncertainty in measuring the length?
The uncertainty of measuring the length.
So can you measure the length directly or you have to use some calculations?
Oh no, you can just measure it directly, right?
And what is your uncertainty for measuring for measurements?
It's the first one, so it's 0.1, right?
Yeah, the list count. It's a list count, right?
Yeah,
Yeah, that's your uncertainty for length. And what will be the uncertainty for the width?
it'd be the same thing because you're not calculating.
It's just a width, right? 0.1
Yeah.
there.
Okay, sweet. Okay, thank you. Sorry, I was confusing myself.
Okay. Any other questions? Anyone? Okay. Seems like everyone is good. Okay, so good night. And I'll stop the recording now.